Good morning. So we're going to talk about chapter 6 of stats in year 12, which is called statistical distributions. In other words, it's like how your statistics, how your information, how your results are distributed, how they are spread out. So for example, um, if we talked about the statistic of rolling, the probability of rolling a 1, a 2, a 3, etc., when we're rolling a regular die, well, what would that look like? Well, how would it be distributed? It would have a uniform distribution, wouldn't it, of 1/6 for 1 and 2 and 3 and 4 and 5 and 6. That's probably a pretty obvious one. Sometimes we can work out the statistics ourselves from a situation like this. Sometimes we have to use a rule that is given to us. There are all kinds of different statistical distributions. Um, and what this chapter really does is it just continues with the idea of thinking of probabilities and looking at statistics in a more theoretical way. So at the start of statistics, we talked about, collecting results from weather stations, maybe making a box plot or something. Making a box plot, finding the interquartile range or doing some kind of linear interpolation, something like that. That was more focused on sort of real pieces of data. Whereas here we're talking about theoretical situations like flipping lots of coins, rolling lots of dice, stuff like this. So we already started to examine this with probability in the previous chapter. We're going to look at how distributions can be spread out in different ways. And in general, there are two main ways that you will look at. In year 12, you will look at something called the binomial distribution. This is when there are sort of two outcomes, okay? And what this looks like. This links quite closely with the pure chapter as well that you may have done on the binomial expansion. What else? So in year 13, we tend to talk about something called the normal distribution. The normal distribution is used for things like average heights and weights and things like this. It follows this sort of pattern. This will make more sense later on. Okay, so this is what we tend to focus on in year 12 and year 13. But before we do this, we will look at using a function that's given to us to find probabilities. And finally, we talk about hypothesis testing, which is where stats starts to get very, very useful indeed. So, as I said, we'll talk about the binomial distribution with a particular focus towards the end, because we use this quite a lot in the next chapter. But at the start, we're going to talk about all kinds of different probability distributions. And for these, we will need to follow some kind of rule and use our knowledge of probabilities adding up to 1 for all the different mutually exclusive outcomes. A little bit of notation in here, but if you just follow along with number 1, it's not too bad at all. Okay, so these are the answers from the entry ticket. And these can probably best be thought of by doing, for example, here, a tree diagram with 3 branches, okay, and so on and so on. Here, 2 fair dice are rolled, so you might want to represent this with a sample space diagram. 1, 2, 3, 4, 5, 6, and again 1, 2, 3, 4, 5, 6, and look at the different possibilities for when you add the scores together. So 2, 3, something like this. Okay, that's probably the best way to do those. So probability distributions. Here's the idea. We are going to have sort of like a number of different variables, x, that we are going to measure. So you're already kind of familiar with this, although it might just be presented in a different way. So imagine you have a questionnaire, for example, and you're asking about people's favorite colors, red, green, blue, and orange. Well, these are the different variables you are measuring. How many people like red? How many people like green? How many people like blue? How many people like orange? So it's sort of like 4 questions in one, if you want to think of it that way. Underneath this thing here, this is really just another way of writing probability. Okay, so the probability of red, the probability of green, and so on and so on and so on. What does this notation sort of really mean? Well, this capital X, this means the outcome of like a single experiment or a single trial. So what does it mean? imagine we're asking people what their favorite color means. So it means the outcome of asking a question being the same as one of these things is 0.3. The outcome of asking somebody's favorite color being green is 0.4, and so on and so on and so on. So the probability that the outcome of the question or the result when we, roll some dice or flip a coin or whatever, the probability that that is the specific thing that we are looking at, the specific thing, whether it's red, green, or blue, well, that's how we can represent that. This is really just sort of another way of saying this, but you will see this being used quite a bit for this chapter. Okay. So X means like the outcome of a single trial or a single experiment. So later on, if you see this, I think some of the questions have this. This might be like the outcome of the first. This might be the outcome of the second time that you do it, and so on and so on and so on. Right. Shall we start? Yeah. I think I'm going to come back to this one later. So let's just begin with a situation that we can kind of find the probabilities out. So the random variable X, so like the outcomes that I'm measuring are the number of heads when we toss the coin. Okay, so I'm not measuring tails, I'm only measuring heads. Well, if I flip some coins 3 times, these would be the outcomes, wouldn't they? And I mean, you could make these from a tree diagram, or you could just be very systematic with it, with how you're listing these out. Okay, so the best way to do something like this is maybe start with all 3, then start with 1 not being it, and then shuffling this one through. Okay, that's the way that I would recommend doing it. And then maybe you say, well, this is all of the cases of 0 heads. This is all the cases of 1. And then maybe you say, well, I'll do the 2s now. So it could look like that. Shuffle it through. It could be like that, or it could be like that. These are all the cases of just 1. And then there's a case of 0. This can be a good way to systematically find all the results. As long as there's not too many, as long as you're not doing it 4 or 5 times, in which case you wouldn't really be expected to do this. So we can show this as a table. So this table might look a little bit not like you're expecting, but remember, the thing that we're measuring is the heads only. We're not looking at tails, it's heads only. So we've just seen you can either have 0 when you have tails, tails, tails. You can have 1. These things here all had 1. You can have 2. These things here all have 2. And you can have 3. Okay, and in this case, we can actually get our probabilities from the situation. So there are 8 different outcomes, and then the number of times that we see them. Okay, but we can represent this actually as a function as well. This doesn't just have to be a table. We can represent this as a function, and this might be quite useful for reasons that we'll talk about a little bit later. So the probability that the outcome is the thing that I'm measuring is 1/8 when X is 0 or 3. Well, look, when it's 0 or 3, you get those outcomes. The probability that the outcome is the thing that I'm measuring is 3/8 when X is 1 or 2. Well, that's those ones there. It's 0 otherwise. This is important. It needs to be defined. You need to state clearly what your domain is, what the values of X that you are looking at. So we know, for example, that 4 is not something that you can get. -1 is not something that you can get. 1.5 is not something that we can get. So we need to say that it's 0 otherwise. Unless it's 0, 3, 1, or 2, the probability of it is 0. Okay? And that makes sense because if you add all of those up together, you get 1, don't you? So that must be all of the different things that can happen, because mutually exclusive, these separate events, their probabilities must add up to 1. So pause the video and have a quick go at this one here. So read it carefully, because in this chapter, If you do sort of have dice, they'll often be biased. So just read the question carefully, think about the situation. Okay, so I'm going to assume that you've had a go now. So 1, 2, 3, 4 are all an eighth. Okay, well, together they will add up to 4/8 then. The probability of a 5 or a 6 is equal. So if I know that they all must add up to 1, 5 and 6, well, there's a half left, and that half will be split evenly. So I must have eighth, 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 quarter, quarter. Must be the way that it's distributed. Okay? Because they've all got to add up to 1. As a function, how would I write this as a function? Well, it needs to say the probability that the outcome is the variable x that we are looking at is an eighth for 1, 2, 3, 4, because it's the same for all of these. The probability is 1/4 for x equals 5, x equals 6, and there are no other possibilities. So 0 otherwise is what we're looking for. Okay. So that's sort of like when we can make the sample space ourselves, when it's a nice event that we can create. But that's not always going to happen because we're looking at all kinds of different distributions now. And one of the things that can happen is we can actually be given a rule that we need to use to find the probabilities. Okay, so here, there's no talk about, oh, we're flipping coins or spinning some spinners or anything. None of that stuff's going on. So you don't have to make the probability from your understanding of a situation. You need to make it by using a function. So the probability of something happening is 0.1 multiplied by the variable that we are measuring itself. So what does this mean? It means if you want to find the probability that that the outcome is 1 in this case, you need to substitute the 1 into this here, and you will get 0.1 times 1, which is 0.1. Okay, so you use that there, you use the algebra, you use the function to make the probability. What about when it's 2? Well, for that one, you would substitute 2 in. And for 3, you'd substitute in 3, and so on and so on. And you'd end up with these probabilities here. So the distribution, what does the distribution look like? It looks like this. This is how the distribution looks like. So you're more likely to get a result of, 3 or 4 than you are for a number like 1 or 2. In fact, 4 has the highest probability out of those 4 variables. Okay, what's the advantage of this? Well, later on when things get a bit more complicated, because this data, you may have realized that all of the data really we've been looking at so far is discrete. Yeah, whole numbers are discrete data. They have like a smallest unit, which is a 1, a unit. This is discrete data. So this is okay for this if we have like 4, 5, 6 numbers. It's okay. Even with like 5 or 6 numbers, though, it's going to start to take you quite a long time. Later on, it would not be practical. Okay. So what we can do is we can use functions. So the idea is that a function is a neater way of representing this. Okay, instead of having to like calculate everything individually. Tables, well, I mean, the table, it's nice and clear, really, isn't it? What your probabilities are. Yeah, notice again, they still add up to 1. So, 0 otherwise. There are no other situations that we're talking about. So let's do another one of these then. So we've looked at ones where there's an underlying sample space to understand it. And now we're looking at ones where we have to use a function, where we have to like calculate our probabilities ourselves. Yeah, just worth saying here, you probably won't have seen this unless you did further maths before. This symbol here is just used to say like, oh, there are 2 different directions. Okay, so you have this rule if you're 1, 2, 3, or 4, or if you have 0, sorry, if you have another number, then it's 0. So you're allowed to have a question where you have like 2 different rules at the same time. Okay, so lots of questions will look something like this. So the notation's changed here. Before we had this, we've got the one above now. You should be pretty comfortable with that now. Really, it just means the probability. So the probability is, and we've just been given this rule here, okay? You could sort of argue the notation is a little bit incomplete. Perhaps it should sort of say something more like this. K over x when x equals 1, 2, 3, 4. I'm just getting this from the question at the top. 0 otherwise. Yeah, if you wanted to make it fit the notation, that's how you would write this. So what we're going to do, well, pause, have a think about it for a moment. And if you think you've got it, trust your instinct, keep going. What we're going to do is we are going to put these numbers in here, one by one, to generate our probabilities. K is just a mystery number here, okay? We don't know what the number is. So if we do this, 1, 2, 3, and 4, well, K over X, if X is 1, is K over 1. K over X, if X is 2, is K over 2. K over X, if X is 3, is K over 3, and you know what the last one will be. So, okay, how does that help us? Well, it helps us because we know something about the sum of these probabilities, don't we? The sum of these probabilities should be 1 because nothing else can happen. All of the sum of all of the mutually exclusive outcomes is 1, or mutually exclusive events, I could say as well. So if we do this one here, you can see that we will be able to solve what K is, okay? Just easiest way is to multiply them all by 12, the LCM. You get K equals 12 over 15. So find the value of K. Well, part B, give the probability distribution in table form. Well, what would you do now? Well, you need to put the result in. So if we put those results in, we'll get something like this. Just a quick note, I'm just going to talk to you about a tip for how you would do this one here. If you say this is going to be K over 2 and you substitute the number in, 12 over 25 over 2, when you're faced with a fraction on top of a fraction, I would always recommend that what you do is you write this out separately as 12 over 25 divided by 2. Take this here to mean divided by 2. Then what you do is you do your keep, flip, change thing. Okay. And you can see you're going to get 6 over 25. Okay. So this does happen sometimes when you're doing A-level maths. This is just how I would handle it. Okay. So pause and have a go at the question on the screen. Remember, the sum, this here means sum. I don't think you've seen this symbol yet. This sigma symbol means sum. So it means if you add up all the probabilities, you will get 1. So use that along with the function that's been defined here to show that K equals 1 over 6. Pause the video, have a go. Okay, so I'm assuming that you've done that. You should get 6K here. 6K will be equal to 1. So K is 1/6. And finally, we can start to introduce the idea then of not probabilities of one particular event, but multiple ones. So if I asked you, what's the probability that the outcome is greater than 3? Well, what am I talking about? What's greater than 3 here? Well, it's 4 and 5. So we could just add those probabilities there. What about at least 2, but less than 4? At least 2 means it includes 2, includes the 3, but less than 4, it doesn't include the 4. Okay, so we could do something like this. And if somebody sort of tries to obfuscate, like to make it unclear what's going on, well, take away 1 from both sides, divide by 2, you'd get that. What's the probability it's greater than or equal to 2.5? Well, there is no 2.5, so the 2.5 bit is kind of meaningless, being equal to 2.5. Above 2.5, though, is 3 and 4 and 5. So you could add those ones together. You'll see a lot more of this later on, especially with this inequality, this sign around. Our calculators later on will do some of this for us. They will add probabilities when we carefully type things in certain models, and they will use this symbol here. So I would just encourage you, when you start to see questions like this as an extension, to start thinking about, could they be expressed somehow in this way as well? So going back to our turn, just pause the video and check these ones here. So check that you group the correct probabilities to add together here. They are mutually exclusive outcomes. So if you want 1 and 4, well, you just add them together. That's the rule for mutually exclusive outcomes. Okay, so no great surprises there. Greater than 4 is not possible. Multiple choice question. Take a bit of time and pause the video. Trust your instincts. You will get some very large numbers. Use your calculators to simplify it down and see if you can get one of these outcomes here. Remember to put the numbers in and then all of the probabilities. So all of the probabilities added. So all of the probabilities added together should be equal to 1. Pause the video. Have a go. Okay, and you should get this one here. If not, just check carefully that you've multiplied everything appropriately. Okay. A few last things. Well, we talked about this case here. This is a special case. I believe the language comes up in the exercise for 6A. Discrete. It's discrete because it takes, in this case, it takes integer values. Integer values and nothing below that, that would be discrete information. Uniform, it's uniform because it's all the same. Okay. And I think we'll leave the other ones for next time. So just that one there to keep an eye on for now. Okay, and that takes you up to 6A. A couple of hints to help you answer on the screen. Careful for number 9. I believe for number 9, it talks about outcome 1 and then outcome 2. That's what this language here means. Okay, best of luck.